Okay, so welcome students. As promised, I did say that I'd go through a practice problem from your homework, and here it goes. So it's number 6. A championship golfer uses a 9-iron to chip his shots right into the cup. It's very pertinent with the Ryder Cup and our rear view mirrors here. If the golf ball is launched at a velocity of 20 meters per second at an angle of 60 degrees above the horizontal. Part A, how long was the ball in the air? Well, as per usual, it's very, very important that we sketch out this scenario. And here's a little sketch of the ball as it might pop through the air, go through the air in a parabola with two-dimensional motion, a little bit in the purple X direction and a little bit in the Y. And of course we talked about how the X component of the motion is not changing. It is constant, the velocity is constant, whereas this Y vector is getting smaller until it hits the arc and then changes direction. So it is acceleration vertically but not horizontally. So how do we find out the first question, which is how long the ball was in the air? Well, we're going to think vertical. So the ball has traveled all the way to the cup and has landed in the cup. Hooray. We are assuming that the ball lands on the same horizontal as it began. So in other words, this delta dy, which you sometimes see, that is equal to 0, that it's landed on the same height that it began. So if we think vertical, remember we need 3 variables. We're trying to find delta t. We don't know what it is. We have delta A, which is negative, normally according to sign conventions that we've talked about in class. VIY. Now it's important that we note that the VIY, the initial velocity in the Y, actually is a component of your total initial velocity, which was 20 meters per second. So we'd split it up into the X and Y using trigonometry, and we should see that we have a right angled triangle. So basically the right angle triangle is here. We're treating this initial black vector as 20. That didn't come out very well, but that's 20 meters per second, and we know theta, the red angle there, is 60. So we can isolate for the purple, which is the brown, which is the VIY, and it's VI sine 60, which comes out as 17.32 meters per second. Okay, now we've got 2 variables. We can make an assumption here. Whatever the velocity in the Y direction is at the beginning, at the very end, provided we're assuming there's no air resistance and that the ball lands at the same height as it began, we can say that the velocity Vfy is the exact same magnitude but just in the opposite direction, so just with a changed sign. So we're going to write that as negative 17.32 meters per second. Now we can use one of the big 5 here to isolate for t, and we're going to say Vf is equal to Vi plus At. We know that to be the case in the big 5 from previous, and so a little bit of algebraic magic is going to give us T is equal to Vf minus Vi over A. So in this case, our delta T is going to be equal to negative 17.32. Then we're taking away our VI, which is on this side, which was a positive, but we're taking it away. And the upshot of that is you're going to have this velocity value is doubled, and that's all over 9.81 meters per second squared. What you actually get is a figure that's 3.5, I believe, and it's 3.5 something, but we use significant figures to denote that there's only 2 here. So the delta t, the time for the ball to go up and come back down and land at that position, is 3.5 seconds. Now all of that was done by thinking vertically. Now what if we have to get the distance traveled along the horizontal? So this delta dx in purple here. So how far along the horizontal did it go? Well, remember a couple of key points here. You split the original vector into its x direction, into its x component, and you get Vi cos theta, or Vi cos 60 in this instance. And we also need to remember this simple equation because there's constant velocity. And hopefully, because we have delta t and we can get Vix, we can solve for the third variable here, which is delta dx. So we're going to just substitute in that value for Vix. We have Vi cos 60, which is 10 meters per second. And that's the portion of the initial velocity that was in the x direction. And we have the value for t here as 3.5 seconds. Now, of course, we're never ignoring our units here, so we have meters per second multiplied by second. Of course, we can cancel those. And that's going to leave us with a nice, tidy number of 35 meters. Okay, so that's what you should have got for B. Now for part C. Part C, what are we being asked? What maximum height did the ball reach? Okay, so the question here is, what height, what maximum did the ball reach? Which I'm going to say is around here. Now, a couple of things at the maximum height. We talked about previously in class how, of course, there's still a velocity in the x direction, which is the same and unchanging, unwielding, but there's now nothing in the y direction. So at this particular point, as the ball has flown and taken its time to go up this part, which is, we're assuming is half of the adventure here because the ball has arrived back down at the same height, Vfy would actually be equal to 0. So that's an important point here, that Vfy is equal to 0. So how are we going to get this? Well, Vfy is equal to 0, so that allows us, that gives us all the variables that we require to answer this question. So what height did the ball reach? So what we're actually looking for is delta dy. We don't know what height it's reached. However, what do we know? We do know Viy is equal to 17.32 meters per second. We're not interested in the x direction at all. We do know A is equal to negative 9.81. And we also do know Vfy at this particular point is equal to 0. Okay, so we have those three variables. We have three variables. That's what we need. So which one of the big five are we going to use? Well, how about this one? Vf squared is equal to Vi squared plus 2a delta d. Of course, we're looking for delta d, and so with a little bit of algebraic magic again, or of course core mathematics, we will say Vf squared minus Vi squared all over 2a. And that's just rearranging. That's rearranging the equation that's above. So this equation, by bringing the Vi over to the other side and then dividing by 2a. So bringing the Vi and then dividing everything by 2a. And that's equal to Vf squared, which is 0 locally, minus Vi squared, which is 17.32 meters per second squared. Squared, so 0 minus that squared all over twice, and you're going to get a negative 9.81 meters per second squared. Okay, so you probably see a couple of things here. We'll get a negative and a negative, which will turn a positive, which is what we would hope to see because it's in the y. So let's just see what our answer is now. So we're going to square 17.32. We're going to hit x squared equals, and we're going to divide that by 9.81. And we're not forgetting the 2. So if you do that, you get 30. But you've got to come along and divide by 2 also. And so that gives us 15.28. So we come out with 15.28. You'll notice a couple of things that's really important here. That 15.28 is a positive. Okay? And it's 15.28 meters because of displacement. The other thing to note is that how does that relate back to our original picture? Well, what it means is that at its absolute maximum height, that this red portion, the y portion here, was 15.28 meters. and that is a positive because it's positive in the y direction. Okay, so that is everything that we needed to go through. We will go through maybe 1 or 2 questions in the next day. So if you've got any questions in the meantime, please do not hesitate to let me know.